Okay, so let us now apply the concepts or the rules that we derived from the previous discussion. Let's just solve some complicated block diagrams and reduce them into a more simpler or in canonical form. We can determine the transfer function of the whole system or simply reduce them into the canonical form. So let's take this example. Determine C over R and maybe B over R also. B over R, this is the feedback ratio. This is the control ratio or the transfer function of the system. Of the block diagram that is given. So this is the block diagram. Let me draw it. Determine C over R and B over R of this block diagram. So here, let's start with a simple block diagram. So this is a simple block diagram. First, we need in the rules before you reduce block diagram. You can take some steps. The first thing that you do is look at for some cascaded blocks in the block diagram. So you start with them. Start reducing cascaded blocks. So for example, in our example here, this is a cascaded block. Here, we can reduce it into just a one block. And we already know how to reduce them into just one block. So we have G1 and G4. So in one block, this is just G1 times G4. So that's the first step. Look for some cascaded blocks and convert them into just one block. Second step is to look for the parallel blocks. Then parallel blocks, this is not a parallel block here, this is canonical form. But this is a parallel block somewhere here. So let's use another color. Let me use this one. This is a parallel blocks. They are in parallel G3 and G2. So we can combine them into just one blocks, and we already know how to do that. We did that in the last discussion here. So parallel blocks. So how do we deal with parallel blocks? So remember, parallel blocks, we just add the gains. So you just add the gains. So in our example, the gains are G3 and G2. So this one now will be just equal to G3 plus G2 or G2 plus G3. Next, after that, we also want to look for some canonical form that is inside the system or the block diagram. And where's that canonical form here? This one. We can also reduce this into just one block. And reduce this one into just one block. And this looks like just a canonical form. This is one block in the forward path, and this is the feedback path. This is our G. So in our formula for a canonical form, C over R is just equal to, remember, C over R, canonical form. It's just equal to G over 1 plus or minus G times H. Where plus or minus is, it depends on the sign here. So this is plus and plus, so here should be minus 1 minus G times H. So this one now here will be equivalent to G or G's. G1, G4. G1 times G4 all over 1 because this is plus, so this should be minus 1 minus G times H. Our G is G1 times G4 and our H is just H1 times H1. So this purple one here is just equal to this transfer function. So if we simplify now, so we just have 3 blocks. So we reduce this into just 3 blocks. The purple one, Then we have this. What color is this? The orange one. I have the orange one here. And we have our H2 somewhere here. So this is now the equivalent block diagram. Then we have a feedback. Our feedback here is this H2. Then this is R minus, this is minus, this is plus R, and this is our C. This is the purple one, and this one is this one. And again, this is cascaded. So we can simplify it again by multiplying them because they are cascaded. So this one times this one. So the equivalent now, the equivalent of these two here will be the product of the two, which is equal to this one. So G1, G4 times G3 plus G2 all over 1 minus G1, G4, H1. Then from that, this is now the canonical form. It's now in canonical form. You can erase this. Then I'll change this, just copy this one and put it there. Copy, paste. So this is now in canonical form. So what will be our C over R? So we can now solve for our C over R using again our formula of C over R. So C over R, or the control ratio, is just G over 1 plus minus GH. G is the transfer function at the forward part, and H is the transfer function at the feedback part. So H is just H2, and this will be our G. And it's minus, so this will be equal to G, which is G1, G4 times G2 plus G3 all over 1 minus G1, G4 times H1. And this is all over 1, so this is minus, so this should be plus G times H. So just copy this. This is our G. Then I multiply this with H. Our H is H2. So just multiply this with H2. Then this will be the C over R. We can simplify this if you want. So to simplify this one, we can add the denominator. The denominator will be equal to, so let me just copy this again. Paste. So I'll just change the denominator. So here, I'll just multiply it. The LCD will be 1 minus G1, G4, H1. So I need to put it here. 1 minus G1, G4, H1. Then plus the whole thing. And so that we can cancel this out. And our transfer function now, C over R, will be just equal to G1, G4, G2 plus G3 all over 1 minus G1, G4, H1. Then we have plus G1, G4, H2 times G2 plus G3. And this is okay. This can be our transfer function, C over R, the control ratio, or the closed loop transfer function. So that's how we simplify this more complicated than a canonical form into a simpler transfer function. Just a single transfer function. That's the equivalent of this whole thing. For B over R, so remember our derived formula for B over R. C over R is G over 1 plus or minus plus GH. For B over R, this is just equal to GH all over 1 minus or plus minus G times H. And if you look at C over R, our formula for C over R is this one. So you just need to multiply this by H. So you just take this this one, and you just need to multiply it by our H. And remember, our H here is H2 in the canonical form. So B over R now, B over R is just equal to this one times H2. So it will be the feedback ratio. Then for the error ratio, remember E over R, it's a different formula. This is 1 over 1 plus or minus G times H. So if you want to solve for that, you just need to remove this one and retain this. Or simply you inverse this to here. So we can just write that. So E over R now will be equal, just add it, C over R and also E over R. E over R is just equal to this one. Then this one divided by this one, because this will be 1 here at the numerator, and this is our denominator. P. Then I paste it here. So this will become our denominator. And for the numerator, it's this one, 1 minus G1, G4, H1. So that is the error ratio, or the actuating signal ratio. So if you want to solve that. So in other words, if you would simplify that into just the canonical form, you can determine these 3 parameters. This is the first example. And this is the simple example. Let's try more difficult one, more complex example. Or before that, complicated. What if we're given with the transfer function here? So instead of G's and H, it's the actual transfer function. So let's say here this block is just equal to 1 over S plus 1. Then we have another block that is equal to 1 over S. And they are cascaded. And we have an output C, and we have a summing point somewhere here. And we have a feedback, which is equal to 1 over S plus 2. That's the feedback. And we have a takeoff point. Then let's say this is a negative feedback. So it can be a positive feedback. It can be a negative feedback. If this is negative, it's called negative feedback control system. It's positive, then it's called positive feedback control system. And also sometimes if you can see some this black here, it's just a straight line. So if you see that it's just a straight line, this straight line means you can put a transfer function. So if you have a straight line just like that, you can put a transfer function here, but the transfer function is just equal to 1. Why? Because the input is the same as the output, because it's just a straight line. So it's just the same. This one is just the same as a straight line. And usually the application of that is in the feedback path. If the feedback path is just a straight line, there's no feedback element here. There's no black here. It's just a straight line going from the output to the summing point of the input. Then we call that the unity feedback control system. It's a unity feedback. So what's the application of that? Especially in electrical engineering, because our output sometimes it's voltage. So if our output is voltage and your input is also voltage, so you don't need to convert that. They have the same voltage. You can compare them already here. You can add them directly because it's a voltage coming from the output. It's a voltage coming from the input. You add them, then you have another voltage. So that's fine. You don't need any transfer function here. You don't need sensors actually. But if it's a different form, so for example, just like the angular velocity or speed, your output is a mechanical energy. It's a mechanical parameter. But here, it's a voltage. So you need to convert that mechanical parameter into an electrical parameter. So you need a transfer function here, which will do that. A transfer function, and that's a generator. It can also be a motor, because motor is from electrical to a mechanical conversion. It's a transducer. We call them transducer. Transducers, these are devices that converts an energy from another form to another form of energy. So a generator is an example of that. And some other sensors. Sensors are types of transducer. There are two types. We have sensors and we have also actuators. Sensors usually they are used in the feedback path, and the actuators usually those are the things that we control. For example, uh, magnetic contactor, relays. Those are the things that we want to control. Those are actuators. So you apply voltage, the output is a mechanical output. That's an actuator. While the sensor is the other way around. You apply certain parameters in mechanical. It can be temperature also, and that temperature will be converted into a voltage that will be feed into this part here, so that we can compare them later on. So we need to go back to electrical signals. It's easier for us to deal electrical signals. We can just program them using our computers if you want. So it's very important for us. Remember, we have also converters, DAC and ADC. We will talk about this later on in instrumentation and control. Digital to analog converters and analog to digital converters, because we are using computers, those are digitals, but our sensors are all analogs. So we need to convert them into another type of signal also in digital and analog. But for now, we don't need to talk about that. We can just talk about that later on. So here, what is C over R? If I want to solve for C over R, what is C over R? C over R is just G over 1 plus or minus G times H. So this is minus, so it's positive. So what is our G? Our G is this 2 here. So what's the equivalent of these two blocks into just one block? So you just need to multiply them. So this is just 1 over S times S plus 1. That's G. Then 1, this is minus, so plus. This G, which is 1 over S times S plus 1, this is our G. You multiply it with H, which is 1 over S plus 2. And simplify this. 1 over S times S plus 1 over 1 plus 1 over S plus 1 times S plus 2. Then simplify further. This will be equal to 1 over S times S plus 1 all over S times S plus 1 times S plus 2, then S times S plus 1 times S plus 2, then plus 1. And you can multiply this times this. So C over R now, the transfer function will be just equal to S times S plus 1, S plus 2, and this one times this one. This will be S squared times S plus 1 squared times S plus 2 plus S times S plus 1. Or we can cancel out. Actually, we can cancel out S and S plus 1. We can do that. S and S plus 1. So that this will be just equal to C over R will just be equal to S plus 2 all over S times S plus 1 times S plus 2 and another S plus 1 here plus 1. So this will be the transfer function now of this one. It's equivalent of this. So you already know how to solve this transfer function. For the individual transfer function, we just apply chapter 2. Then if you combine them into one whole system, then this is the transfer function of this whole system. So that's how block diagram, how useful block diagram is. Then let's take another example of the reduction. So number 3. Okay, determine C over R if H1 is equal to 1 over G1 and H2 is equal to 1 over G2. So we can just substitute this one later on when we derive the transfer function. Or you can directly substitute it first, then you solve it. The other way around, it's the same. It's just the same thing. And this is an easy one because it's just a simple one. We don't have cascaded blocks. We don't have parallel blocks, but we only have uh, blocks in canonical form. So the first one is this block here. They are in canonical form. The second one is this, also in canonical form. Then if we combine them, cascade them, then we have the canonical form of the whole system. So what is this part? This purple one. This is just equal to G1 all over 1, because this is plus, so minus G1 H1. Well, this one, the red one, is just G2 all over 1, so plus again, so this should be minus G2 H2. We multiply them, and that's our total transfer function for the forward path. So if we solve for C over R, now we can solve that directly. C over R will be equal to the product of the two. So this is G1 times G2 all over 1 minus G1 H1. Multiply this with 1 minus G2 H2. Then all over 1, and this is minus, so this should be plus. This whole thing here multiplied by H3. So G1 G2 times H3 all over 1 minus G1 H1 multiplied by 1 minus G2 H2. Then simplify this again. You can cancel out this and this, but we need to multiply it here by the 1. So G1 G2, and we have 1 minus G1 H1 times 1 minus G2 H2 multiplied by, or plus G1 times G2 times H3. And this will be our C over R. But we need to substitute our values for given values. H1 is 1 over G1. H1 is 1 over G1. H2 is 1 over G2. So this part, this will be equal to 1, because H1 is 1 over G1 times G1 is just 1. And also this one is also equal to 1 because H is 1 over G2. And if this is 1, 1 minus 1 is 0, 1 minus 1 is 0. So this whole thing is just equal to 0. So therefore, this is just equal to this divided by this one. So we just cancel out G1 times G2. So our transfer function will be just equal to 1 over H3. So the transfer function of the whole is just equal to, it depends on the feedback of the system, as long as H1 is equal to 1 over G1 and H2 is equal to 1 over G2. So that's example number 3. So that's still an easy example. Now let's take a difficult example. So number 3, number 4. This one. So it looks like a more simpler example compared to the previous examples, but this is harder to simplify. Why? Because there's an overlapping between these two canonical forms. So we cannot just say that this part here is in canonical form. Why? Because we have a take-off point somewhere here. Also this one. So the solution into this one is to apply our rules. We can just move the points here, the take-off points. Or you can also move this take-off point outside the summing point. That's also possible. Or we can move that take-off point, you move it, this take-off point, move it here from right to left of G1, so that this one will be just a normal canonical form. And this one here, this is just a straight line with a feedback of H1. So again, I said before, If it's a straight line, you can just put a block there if you want, and that block is just equal to 1. It's a unity block. So don't worry about that. If you see a straight line in this part, it's at the canonical form, it's at the parallel form. But if you do that, if you move this one here, then this part here will be in parallel. But if I move this takeoff point here, this one will be in canonical form. Okay? This will be in the canonical form, and this one at the top part will be also still in parallel, but it's a unity. The forward path will be a straight line. Or if you move this point outside the take or the summing point, then what happens? So if you do that, this one will become parallel, and it will become just a single block. And after that, we just simplify it in the canonical form. But if I don't want that to move, if this is this point, if I move this point to before the summing point, it's also possible. We simplify first this canonical form into single block. Then after that, we parallel that with G2. So there's so many ways in solving this problem. It depends on what you want and what you remember. You remember of doing. Is it easier for us to move the takeoff point along a block or along a summing point? Hint, it's harder to move the takeoff point along a summing point. So we can just use the first to move the takeoff point along a block. Why? Because we already did that. We actually derived that here. Moving a block, a takeoff point from left to right. So you can use left to right or even right to left. It doesn't matter. But if you use left to right, you need to move, add a block here, which is equal to 1 over G. But if it's right to left, then you just add a block, which is equal to G. So we can choose, so it's more, instead of 1 over G, we can use this one, G. So if we use that G, we are going from right to left. Right to left. We are moving from right to left. So from right to left. So this one from right to left. So we move that. And if you move that, we need to include the one that we're moving, this signal here. We move it here. We need to add a block here, which is equal to this one, G1. So let's do that. So I can just copy this here. Then I can just move this takeoff point into the side. So let me move this. Then erase this one. So this will be at this part here. I can also move this somewhere here. Then you connect them. This is now the summing point and the takeoff point. So this is our takeoff point. We already moved the takeoff point here. So this is our takeoff point. Let's label it A. So this is our new takeoff point A. But we did change the block diagram. And we need to compensate that by drawing another black somewhere here. We need to put includes a black here, and that black, because we move from right to left, this should be equal to G1. This black should be equal to G1. Why? Because we move from right to the left. Okay, then this part here now, you can just treat it as a parallel. Black's G2 is in parallel with G1 because this is take-off points. So they are, we can just simply interchange this. It's fine to interchange the take-off point. So can you put it here, A, it's fine, it's just the same. So that this will be, these parallel blocks now, these two here, G1, G2, and G1. So how do we simplify them? That is just, we add them. So this is just equal to G1 plus G2. So let's just redraw it again so that you can imagine this. So we have a straight line here, or just like what I said, you can also put so that it looked like a canonical form. So Ctrl C. Let me draw a block here, which is equal to 1. Then this will go at this point until G1. Then we have another block here, which is equal to H1, and another block, which is the purple one that we had. And this is our new take-off point going here. And this is plus, this is R. This is our A here. Then we have another take-off point here, which will go to G2. This is G2 and goes back to the summing point. This is plus, and this is our C. So that's how we simplify this into this form. So if you look at now, this one, it's obvious that we have two blocks here. We just cascaded block. The first one is this one. The second one is this one. And they are cascaded. So to solve for C over R, we just need to multiply these two transfer functions. So what's the purple one? So this is in canonical form. Our H or our G here is 1. Or we have here a, we need to simplify this first because they are in cascaded. So this is just equal to G1 H1 because they are cascaded. That is our H and this is our G. So the transfer function now C over R is G over 1 plus or minus GH. This is plus. So G is 1 all over 1. So this is plus, so this is minus 1 G times H. And H is G1 H1. G1 H1. And that is our transfer function for this one. And for the red one, this is not a canonical form. It's a parallel blocks. So the two of them are parallel. So if they are parallel, it's like what we did before, we just add them. So this is just equivalent to G1 plus G2. And these are two blocks that are cascaded. So to solve for C over R, we just multiply them. So our C over R now, C over R will be just equal to the product of the two. G1 plus G2 all over this one. 1 minus G1 times H1. So this is our transfer function. Okay. Next, let's take another one. Let's take one more last example. Harder or more complicated block diagram. So let's just, this will be number 5. Determine C over R. So let us solve this. So this is a more complicated block diagram. C over R. So for me, we can interchange also. the summing point. It's the same as the takeoff point. We can just interchange them and nothing will happen. Because if you look at this, so if you add, this is x and y, x plus y, then this will be, if this is z, x plus y plus z. If you interchange them, it's also still the same, x plus y plus z, so it doesn't matter. So you can just interchange them, just like the takeoff point. So I move this into this point here, so that this one, H2 and G2 will be in canonical form. So we can just make that one a single block. You can just copy this here, then simplify it. So what I do is move that, interchange this point here. So instead of here, so this will be minus. Remember, this is minus. Oops. So I will put it here. I will move that here. Also, I move this. Or let me just erase this one. I slightly move this one here. Then draw it again. So this will be our new block diagram. So remember, this is minus and this is still minus. So we interchange the summing point. So here, we just interchange them. Why do we need to do that? Because this is now a canonical form. We can simplify this into just one block. And that one block, this is just equal to G2 all over 1. This is minus, so plus G2 times H2. And again, this is one block. And we have a point here. I take a point. The next step that I'll be doing is I move this takeoff point into this point here, so that we have this block in cascaded with this block. And after that, if they're cascaded, after it will be in parallel with H3. And after H3 in parallel with the cascaded equivalent of these two, it will be again cascaded to G1. And after cascaded to G1, then it's the canonical form. In canonical form with H1. So that's the process. Yeah, we just need to do that. So we move this takeoff point into this point. So we are moving from left to right. So what we do is, so from left to right, so remember from left to right, left to right. So if we move or the takeoff point from left to right, so this one to this point, so what we do is we multiply or we put 1 over G in the branch that we are moving from left to right of the block. From left to right of the block. So we need to put a block here. We need to put it here. And this should be equal to 1 over G3. But why G3? Because we're moving along G3. I move this one into this point. So I need to compensate this with 1 over G3. Let's do that. Then after that, it's already done. So we have G1 here. Then we have a summing point. So this is now just one block in cascade with a G3. And I already moved this branch here at this point. So this is C. So we have 2 takeoff points here. The other one is going to H3. While the other one is this one. So we need to put here 1 over G3. Why 1 over G3 again? Because this is G3. We're moving along G3. And we have still H1 here. Then this is minus, this is plus, and what is this is again? This is plus and minus. This is our R, and this is our C. And this one is G2 all over 1 plus G2 times H2. And just like what I said, this is in cascade or in series. To solve that, you just multiply them. G2 times G3 all over 1 plus G2 H2. Then the next thing that I will be doing will be this part. So combine them, they are in parallel. These are in parallel. So this one is in parallel test. Or is it parallel? It's not parallel because the summing point actually is in the left side. It's not at the right side. So we can just move H3 at the bottom, then it's a canonical form. It's actually a canonical form. It's not a parallel block. So it's a canonical form with G. This is our G, and our H is this one. So this purple one will be equal to G. What is G? G2, G3 all over 1 plus G2H2. That's our G all over 1. This is minus, so it should be plus. Plus what? Plus G times H. This is our G. So G2, G3, our H is H3. H3. So I just multiply the numerator by H3. Then I'll divide it again by 1 plus G2 H2. And this will be the transfer function of this purple one here, which is in cascade again with G1. And in canonical form with the cascaded equivalent of H1 and G3. So H1 over G3. Let me first simplify this purple one here. So it will be, she'll cancel out here. So G2, G3 all over 1 times that, 1 plus G2, H2 plus G2, G3, H3. So that's the purple one. And it should be in cascade with G1. So the whole forward path transfer function will be just equal to G2, G3 times G1. Why G1? Because this is in cascaded with the purple one. All over, this is the same thing. 1 plus G2, H2 plus G2, G3, H3. So this is our equivalent block in the forward path. And for the feedback path, it's the product of the two, H1 all over G3. So we have a summing point, go back here, take a point, then we have an input R, output C. This is minus, that's plus. So we can now solve for C over R. So our C over R now will be equal to this one, G1, G2, G3, all over 1 plus G2H2 plus G2, G3, H3, all over, because this is minus again, so it should be 1 plus this one multiplied by this one. So H1 over G3 times this, G3 will cancel out, so we only have G1, G2 times H1. G1, G2 times H1. All over 1 plus G2, H2 plus G2, G3, H3. And simplify this again, cancel this out. And this will be G1, G2, G3, all over this one times this one. 1 plus G2, H2 plus G2, G3, H3 plus G1, G2, H1. And this will be C over R. C over R. So that's how complicated this one is. But if you know how to move these points, summing points, take-off points, it doesn't matter. Now, in some cases, for the block diagram, we also have what happens if we have just more than one inputs. It's possible to have more than one input. We have systems that are called usually single input, single output, SISO. This is single input, single output. But it's also possible that we have a multiple input, single output, MISO, MISO. Multiple input, multiple means more than one, but still have a single one, single output. Or it's also possible to have multiple input and multiple output. Some also, they call it BIBO, bounded input and bounded output. The input and output are bounded. So these are terminologies in control system that you will be encountering later on. And their meaning are obvious, single input, single output. So if you have more than one input in your system, what will you do? If you want to solve for the output of the system, just like what we do in circuits, also in electromagnetism, we can apply superposition theorem. So what is superposition theorem? You remove all the sources. In circuits, we call them sources. But in this one, in block diagrams, we just remove all the inputs and retain one. Remove them all except one. Then solve for the output. C. I call that C1. Then repeat that process for all the inputs. You remove that input, you bring back another input. Then solve for C, or call it C2, and so on. So if there are 4 inputs, you do it 4 times. C1, C2, C3, and C4. Then after that, the total output will be just equal to the sum or the net of the different effects of different sources or inputs. So you just add them all, C1 plus C2 plus C3 plus C4. So let's take this example. This is really the last example now for multiple input, single output system. Number 5, number 6. So if you encounter this type of systems, so you know how to deal with them. So we have, let's see, here. 1. Then you have another input here, another input here. So these are 3 inputs. We have input somewhere here. Let's call it R. This is the legit input because in actual practice, our system are prone to some outside interference. So our input here is just really R, but there are some noises that is changing our system. So if you design the control system, you need to take into your design the noises that are unpredictable. Those are unwanted signals. So your system should be a robust system, so meaning it can adjust itself, and it depends, even if there's a noise or disturbance in the system. So you have an input R here. Let's call this one U, because this is between that, because this is 2, U1 and U2. And let's say this is plus plus, and also plus here. And positive feedback. Let's call this G1, G2, and then H1, H2. And this is C. Determine C. So we need to determine the output. So how do we do that? So again, the transfer or superposition theorem, we need to remove first all the other except one other inputs. So we can start with R. You remove U1 and U2. So if you remove U1 and U2, so the only signal that is going through the summing point is this signal here. So this one plus this 0 here will be equal to this one. So we can just remove also the summing point. We can just make it a straight line. So the system will be, so this is, if this is a straight line, then G1 is in cascade with G2. H1 is in cascade with H2. So G1 times G2, H1 times H2. So that's the canonical form. So retain R. The output due to R now, let's call it CR, will be just equal to what? CR over R. This is our G1 times G2 all over, this is plus. So 1 minus G1, G2, that's our G1, G2, our forward transfer function, multiplied by the feedback, H1 times H2. And this is now the output due to R. So now next is we repeat the process, but this time we remove R. So if I remove R, this will be a straight line. And remove U2, so retain U1. So what will happen? So if you can imagine this, retain U1 and solve for C. So if I redraw this, this will gone, it will be removed, and we have, and this will be the only input, U1. Then we have another one here. This will be just a straight line. Then connect it here. This is plus, plus, this is G1, and this is G2, H1, and H2. So where is C? Our C is here. This is our C. So you can also, again, redraw this. So if you rotate it, you rotate this U, put it here, G1, H1 will be at the feedback path. This will be our feedback path. Can you imagine this? This will be our feedback path, because it's our input now. And this is the forward path. This is our forward path. So meaning this is our G, while the cascaded equivalent of this 3 is our H. So if we solve for C with respect to U1, C over R, or C over U1, this will be just equal to G. Our G is G2 all over 1. This is plus here. So this should be minus our G, which is G2, multiplied by our H. Our H is the cascaded block here. We have G1, H1, H2. So you just multiply that with that one. G1, H1, H2. And that will be our output with respect to U1. And lastly, for U2, so if you do that again, if you repeat the process, if this is my input, so I rotate this one, put it here, this summing point. This will gone, this will gone. Our summing point here will go here, and that will be U2. Then our feedback, what will happen to the feedback? Our only feedback now will be H2. And our forward path will be H1, G1, and G2. So retaining, we can just solve that. Retain U2. So C over U2 now will be, what will be our G? Our G will be H1 times G1 times G2. H1, G1, G2. All over 1. This time, this is still minus. This is still plus, plus and plus. So it should be minus here. Copy G1 or G, H1, G1 times G2. And you multiply it with the feedback. Whereas a new feedback now, this output or input is this one. So the feedback is just H2. So you just multiply this with H2. And that will be the output due to U2. Then for C is this equal to, or this should be C, let's just call it C1 and this one is C2. C will be just equal to C or plus C1 plus C. So C is equal to C1 here, this one. Then you multiply it. This is the transfer function with respect to R. C1 is, this is our C1. You just need to multiply it by U1. Then plus, multiply it by U1. And lastly, for the output due to U2. Then plus, you multiply this with U2. And that will be our output C. So that is how we deal with system that involves two or more transfer function. You can still simplify this if you want, because they have all the same denominator. 1 minus G1 G2 H1 H2 G1 G2 H1 H2 G1 G2 H1 H2. They have all the same denominator. You can just put the denominator 1 minus G1 G2 H1 H2, and we have G1 G2 times R plus G2 times U1 plus G1 G2 H1 times U2. So you can rewrite that into that form. It's still the same. So okay, so that's how we deal with, how we simplify or reduce block diagrams, and also how we deal with system that has more than one input, multiple inputs. So that is block diagram. So next meeting, we will be talking about the other type, pictorial representation of control system, the signal flow graph.